This is the continuation of lecture number 2 here in Unit 10. We're going to continue looking at simple harmonic motion, and we're going to start by finishing the equation. The last thing we haven't yet talked about is this last term, which is highlighted in blue. This is the lowercase Greek letter phi, or sometimes it's pronounced phi. Both are correct. And we're going to define it as the phase angle. Before I go into an in-depth discussion of what that means and what it looks like graphically, here's a definition. It's a denotation that the initial position and velocity are different than one modeled by a sine wave or a cosine wave. So I want to first show you an example of why you might need a phase angle. So where does a sine wave begin on a graph? Well, you've seen this before, I'm sure, so I'll just show you. We know that at time 0, the graph of a sine wave is also at position 0, right? You've probably seen this more frequently as, theta here on the x-axis and sine of theta here on the y-axis. But remember, this is just a position versus time graph. It's just that sinusoidal functions are what we use to model simple harmonic oscillators. So at time 0, we have position 0. What about velocity? What's true about the velocity at time 0 on a sine wave? Remember, the velocity is the slope of the tangent line on a curve, or we could say it's the derivative of position with respect to time at that instant. And on a simple harmonic oscillator, that's often abbreviated SHO. So if a simple harmonic oscillator begins at position 0 and at time 0, and it has a maximum speed at time t equals 0, then the sine wave matches the motion perfectly, because that's what a sine wave already looks like. So what about a cosine wave? Where does it begin on a graph? It begins at the highest value or the largest displacement from its equilibrium position that it will ever achieve. And that means at time 0, it's at its amplitude. What about the velocity? Well, once again, we're looking for the slope of the tangent line at the very beginning, which is flat or horizontal and therefore has a slope of 0. So the velocity is 0 at time 0. And so we can say if a simple harmonic oscillator begins at its amplitude at time 0, and it has no speed at time 0, it's motionless at that instant, then the cosine wave matches the motion perfectly. So what if neither sine nor cosine matches the motion perfectly? That is why we need phi. We need to be able to move these waves just a little bit so that they perfectly match any type of motion. So we already looked at this slide. We're going to add to it. Graphically, phi is a horizontal shift. And somewhat counterintuitively, if you have a leftward shift, it's a positive phi value. So as you see in the equation, the sort of generic placeholder way of writing this, at least the way the AP equations sheet writes it, is with positive phi plus phi. So this sort of implies a leftward shift, but of course you can just make it negative if you need a rightward shift. So once again, positive phi is a leftward shift, negative phi is a rightward shift. Go ahead and pause the video and try to solve these 4 parts. Let's go through it, starting from maximum displacement from equilibrium. What's the term that means the maximum displacement? That's your amplitude. And graphically, it's the maximum distance that you ever see the function get from the x-axis. So you can mark the amplitude here, and in this case, it's 1 meter. Although it's never a bad idea to review old videos. So it's also valid that you could measure the amplitude here, right? The distance from the x-axis is the same to -1 as it is to +1. So amplitude is achieved in 2 different directions, but it's equal in magnitude. We want to look for the period next. Remember that on a graph, we're looking for the distance, and I use that word loosely, between any 2 corresponding spots. So for instance, here are 2 corresponding spots from the origin to the spot where we get back to the same position, 0, and have the same velocity. In other words, the slope here at 4 seconds, if you drew a little tangent line, would be the same as it is here at 0 seconds. And so that's why 2 is not the correct period, because even though you've gotten back to the position that you started at, position 0, you have a different velocity because you have a negative slope, whereas you started with a positive slope. Those 2 conditions, again, for period, or for oscillation really, are you need to get back to the place you started and have the same velocity when you get there. That's why 2 seconds is wrong. So 4 seconds is the period of this oscillation. Frequency is usually the easiest thing to find, and that's again the case here. So if you know the period, which we just found, you can just do the reciprocal and therefore if t is 4, we just do 1 over 4, or 0.25 inverse seconds, which is once again known as a hertz. Hertz is the units for frequency. We finally want an equation to model the graph. Here's the known values that we found in the last few slides. But unfortunately, we only know one of the things that goes in the equation, which is the amplitude. I can make a decision now, which is to use sine or cosine, and I've chosen sine. If it's not apparent why, the answer is because this graph starts at position 0 at time 0, just like a sine wave. And so it would be foolish to use cosine because then you'd have to talk about how much it shifted, and there's no shift from a traditional sine wave. Which also means that phi, that's 0, right? This is a sine wave, so we don't have to shift at all. We do need to find omega to finish it. Omega is always found using one of two equivalent equations. One of them is written here, 2 pi over t. The equivalent equation to this just comes from the stuff written up here. 2 pi over t, that's the same as 2 pi times 1 over t. Well, what's 1 over t? That's f. So you could also use 2 pi times f. Either one's fine. And we plug in the stuff we know. 4 seconds was the period, and there's your omega value. Putting it all together, your equation is this. Okay, pause the video again and try to solve these 5 parts. To find the period, we're looking for the distance in time between two corresponding spots on the graph. So it doesn't matter which two corresponding spots we choose, the answer will be the same. So for instance, you could do this as your period, you could do this as your, like you see, it doesn't matter. Each one of these is the same distance in time. It's the same number of seconds from one red dot to the next. And in all of these cases, for this graph anyway, the answer is 16 seconds. The amplitude, or the maximum displacement from equilibrium, is any of these, right? It's achieved in two different directions, one in the positive, one in the negative, and it's equal in magnitude. So it's just how far are you from the x-axis on a graph, and that is 5 meters. To figure out the phase angle, we have to first decide which wave, sine or cosine, appears to have shifted. Does this look like a sine wave that's moved or a cosine wave that has moved left or right? Well, it's really either one, right? And the reason is that sine and cosine are the same shape, they're just shifted. And the way we can sort of use this new idea of phase is that the sine wave is the cosine wave, but pi over 2 out of phase with it. So it follows the same path, but just not at the same time. And therefore, the value of phi, the phase angle, that depends on which sinusoidal function we want to use. So like I just said, it depends on which sinusoidal function we choose. So we have to just pick one in order to answer this question, what's the phase angle? I'm going to start by looking at the cosine wave. Where does a cosine wave begin? At its amplitude. And so the distance we've shifted a cosine wave would be marked here as phi. Therefore, this is a cosine wave shifted left. How much has it shifted left, though? That turns out to be pi over 4 radians. And I'm going to talk on the next slide about how I found that in more detail. But for now, that is the correct answer. And the reason I make it a positive pi over 4 is because it's a leftward shift. And we said earlier, leftward shifts require a positive phi value and vice versa. Okay, what about compared to a sine wave? Well, a sine wave starts here, or at position 0 with a positive velocity. And so the shift is this distance. Okay, so this would be a sine wave shifted left also. How much has it shifted left? You could go through and figure it out using the same kind of steps. Or, here's the really easy way to do it. We know the answer for the cosine wave, right? We just showed that, pi over 4. And I told you a moment ago that a sine wave is the same as a cosine wave, but out of phase with it by pi over 2 radians. So this distance from this apex down to here, in other words, from where a sine wave starts, oops, I'm kind of saying this backwards, from where a sine wave starts to where a cosine wave starts, this is pi over 2 radians. So we can add that to the phi we already found, and the answer is 3 pi over 4. So that would be phi if you modeled the motion with a sine wave. Like I said on the last slide, what I want to do is show you how I got pi over 4 as the phase shift. And to do that, I have to make a really important point. Phi, or this horizontal shift, is measured in radians. It's the shift of the wave. It's not the shift in time. So you may have said 2 seconds, for instance, because this distance here is exactly 1/8 of a cycle, and since we already identified the cycle or the period to be 16 seconds, right? You may have said, well, it's 1/8 of 16, so 2. But it's not a time shift. It's instead a wave shift. So how far is it from the crest of one wave to the next? It's 2 pi radians, right? I mean, that's just the period of a sinusoidal function. So if this distance is 2 pi, all of your phi values will always be measured in this way, in a number of radians. So let's just keep cutting it in half until we get to the answer. Pi radians, half pi radians. And so that's why my shift on this graph was pi over 4 radians from a cosine curve. Let's draw 2 conclusions from that. The first is this. Your phi value is always greater than or equal to 0, meaning that you can have a phi of 0, which just means you don't need to shift, or you're already matching the motion with just a sine or cosine wave. And it can also go to really any value, but it's kind of dumb to go as high as 2 pi or anything more than that because of the periodicity. So let me give you an example. Let's just pick a spot. Let's just pick this very first spot in blue at -6 seconds. Okay, well, what is a shift of 2 pi from right here? Well, that would just be here. And that's the same place on the curve. So once you've moved 2 pi radians left or right, you've just gotten to the next corresponding spot on the curve. There's no reason to shift it. Or another way of stating that is, if you write an equation where the phase angle is 2 pi, you could just have a phase angle of 0 and get the same result. Okay, one last thought about things that limit phi. Again, these aren't like hard limit. I mean, you can write phi to be just about anything you want, but it's just dumb to do certain values. Really, you can always make phi less than pi over 2. And the reason is you can either use sine or cosine. So no matter where you pick a spot anywhere along this blue line, you can say that it is within half pi radians from either a sine or a cosine wave, or sometimes a negative sine or a negative cosine wave, which is the same thing, but just like flipped upside down. So, putting it all together, phi is the number of radians the graph has been shifted. It's not how many seconds the graph has been shifted. When in doubt, draw this first green line I did. Draw 2 pi as from one peak to the next, and then figure out the shift with respect to that measurement. Okay, we're going to now conclude with frequency, which is 1 over period. 1 over 16 is 6.25 times 10 to the -2 hertz. Putting it all together, we can write this equation. So we know a few things already. We know the amplitude, and we know phi. So I'll plug those in, and remember, it's a positive phi because the shift of a cosine curve is left. 2 pi f is the formula for omega. Remember, you can also use 2 pi over t. Either one is correct. Same thing. And I'll just plug in f here. I only, by the way, chose to use 2 pi f because the last time we did this, we did 2 pi over t. So I just want you to kind of get used to doing it both ways. Neither is better. They're just two different equivalent ways of finding omega. That means omega pi over 8. And your final equation, x is equal to 5 cosine of pi t over 8 plus pi over 4. What I want you to try is to write the equation for the same graph, but I'm going to make you use the sine function this time, even though it's more of a shift, just so you get practice using both. So pause the video and try to write the equation. Here's your answer. The only changes here are that we made cosine sine, because that's what we were instructed to do. And then the shift has to be different, because this graph is a different amount of shift horizontally from where a sine wave starts, or which would be here, than from where a cosine wave starts, which was at the apex here. Before you pause the video, I want to show you a trick for how to find phi on some kinds of graphs. So sometimes graphs will kind of out and tell you how much time has passed before a regular curve begins. So like for instance, I've marked here that at 0.2 seconds, we've got the bottom point or the valley of the graph. The valley here would be where the negative cosine function starts. So I'm going to call this a time shift. Don't make the mistake of thinking that this is like a real thing. Like I wrote a disclaimer at the bottom. I made this entire thing up. but it works, and it's all grounded in real math, so don't think it's like fictional physics. Anyway, so we're going to just kind of define it as this letter Q. Does it mean anything? I just don't want to write the words time shift over and over. Well, let's think about what Q, or this 0.2 seconds before the negative cosine curve begins. What does that sort of mean? Well, in terms of the period, which you could figure out pretty easily, the period is from 0.5 seconds to 1.7 seconds. So the period here is 1.2 seconds. This is a certain percentage of the overall period, right? You could say that 0.2 seconds is to the period of the graph is to 1.2 as the phase angle phi is to 2 pi, the distance from peak to peak, or from any two corresponding points. In other words, I'm going to set up a proportion that relates the period and the phase angle. Q, so the amount of time before we start the curve, over the amount of time a cycle takes, period, equals phi, the angular shift, over 2 pi. So you see how these denominators are analogous. T is the amount of time it takes to complete an entire cycle. 2 pi radians is the sort of distance around a circle. It is one cycle. It's one oscillation. So if I solve this for phi, I get 2 pi q over t, and you notice 2 pi over t. Does that look familiar? Hopefully you can spot that that is the same thing we've been using for omega. So I'm going to replace this with omega. Now we have a little expression that can at least sometimes help us find phi much, much more easily if we know how much time passes before the graph begins, or the curve that we want to use begins, negative cosine in this case. Anyway, if you'd like to, go ahead and pause the video and try to solve the rest of this now, and if not, I'm going to go through it right away. So the next thing we need to figure out is omega. Omega is 2 pi over t, 2 pi over, in this case, 1.2 seconds. And just if you want to do this fractionally, I'm a big fan of using fractions when I'm talking about radians. This simplifies to 10 over 6, or 5/3 pi. So now we know our omega value. Using my fictional made-up but totally works equation to find phi, we use q times omega, where q, remember, is the amount of time that passes before the curve begins, like the curve that you're using to model. And I'm using negative cosine, so the negative cosine curve begins at 0.2 seconds. So that's my q. That times the omega value we just found. And I want to do something with units here to show you why the q comes out to be in radians. Because q, remember, is the amount of time that passes. So that's just in seconds. And then this is omega. Well, omega was found up here in the top by doing 2 pi, which is unitless, that's just a constant, over seconds. So you could either just say inverse seconds, which is again hertz, or you could say radians per second, which is what I did, radians times inverse seconds, or radians per second. Anyway, so you get seconds over seconds, which cancel out, and then you're left with units of just radians. And that means that the phase shift in the formula is a measure of radians. It's how much we've shifted the angular position. And that simplifies to pi over 3. That means we can now finish this and put the entire equation together. And there it is. Hopefully this was helpful. I will see you guys on Monday and Tuesday.